Hi Algebra 1 students, this is Miss Penn. On this video I'm going to go over just an overview of exponential and linear functions, as well as introducing you to the idea of exponential growth versus exponential decay. And we'll be practicing with growth and decay in class. So to start, we're just going to examine two really basic functions, one that is linear and one that is exponential. So on the left-hand side, we have a table where n with n and f of n, where f of n is equal to 2n. So if we start plugging in values for n into the function, you can think f of negative 2 would be 2 times negative 2. Which is negative 4. Right, and f of negative 1 would be 2 times negative 1, which is negative 2. F of 0 would be 2 times 0, 0. F of 1, 2. And you could also think about this pattern recursively, right, where if your slope is 2, basically what you're doing each time is adding 2. So whichever way is easier for you to generate the next term in the sequence, or in the table, you can do it that way. So next we would have 4 and then 6. And if I wanted to plot this on the coordinate plane, just be plotting points. So I'd start with negative 2, negative 4. So as you can see, I plotted all the points, and then I can connect them by drawing the line through them. And you could still think about like graphing the line as using your y equals mx plus b form as well. So just to kind of write that down here. So we know this is a linear function. And the general form is y equals mx plus b. And as we can see on the side of the table, we can tell a function is linear because it's growing by a constant amount. And that's that like repeated addition idea. Okay. So now let's think about this other function on the right-hand side, which is an exponential function. And it is f of n equals 2 to the n. So I'm actually going to skip when n is negative 2 and n is negative 1 to start, and start when n is 0. So when n is 0, if I plug in 0 for n, I would get 2 to the 0. And we know anything to the 0 power is 1. When n is 1, I get 2 to the first power, which is 2. When n is 2, I get 2 to the second power, which is 4. And no, you can also generate these terms just by thinking about repeatedly multiplying by 2. So then the next thing would be 4 times 2, which would be 8. And now, to go backwards and to get what's going on when n is negative 1 and n is negative 2, I could go backwards by doing repeated division. So then at negative 1, I would have 1/2, because I'd do 1 divided by 2. And then at negative 2, I'd have 1/4, because 1/2 divided by 2 is 1/4. And so this is exponential. And our general form of an equation, of an explicit equation, would be y equals, or f of x equals, a times b to the x power. And here, the telltale sign that we have exponential, we have an exponential function is it's going to grow by a constant factor. And remember that the word factor means multiplication. So this is where we see the repeated multiplication. So now let's plot the points on our coordinate plane. So I'm going to start with 0, 1. So about there. Then 1, 2. So there's 2, 4, and 3, 8. And then I can also go and like estimate like -1, 1/2 to be like halfway in between. And then -2, 1/4 is like really close to the x-axis. So then I can kind of sketch this curve that goes through those points, and we can kind of see the difference between an exponential curve and a linear curve, which is a straight line. The exponential curve, which starts out slow at the beginning and then starts increasing faster and faster and faster. So before we get into exploring the difference between exponential growth and exponential decay, I wanted to do a quick review or introduction of negative exponents, because they kind of come into play when we start plugging in negative values for n when we're evaluating a exponential function. So we're going to think about two different exponential expressions. The first one is x to the 5th over x to the 2nd, and we can express this in expanded notation by thinking about x to the 5th as being x times itself 5 times. So that would be x times x times x times x times x divided by, there's these little dots in between. They just didn't show up. Divided by x squared is x times itself once, right? X times x. And when we look at the expanded form, we can cancel out x's on top and bottom, because x over x, like something like this, we know x over x is just 1, so that can cancel. And then I have another pair that can cancel. And what I'm left with is x times x times x, which is x to the 3rd. Okay, well, there's also, we have what are called exponent rules. And in this case, the exponent rule tells us that if you have like x to the n over x to the m, you could treat that as x to the n minus m and subtract the exponents. So in this case, that would be x to the 5th over x to the 2nd is equal to x to the 5, that's a 5, hold on, minus 2, which is the same thing as x to the 3rd. And then we can see that like we get the same answer in using both methods, okay? Now, the second example is a little bit different because we're going to end up with a negative exponent. So here, again, we can start by doing the expanded notation where we have x squared on top and x to the 5th on the bottom. So basically, it's going to look exactly like what we did above, except the denominator and numerator has switched spots. So on the top, we have x times x, and on the bottom, we have x times x times x times x times x. And then again, you can cancel out pairs of x's on the top and the bottom. And we end up with, on the bottom, we have x times x times x, x to the 3rd. On the top, we don't have anything left, right? Well, we can think of that as there being kind of like a 1 up top there holding the place. So we can write this as 1 over x to the 3rd. So now let's look at what, if we were to follow this exponent rule of x to the n over x to the m by subtracting. What do we get here? So we have x to the 2nd over x to the 5th, and we would get x to the 2nd minus 5th, which would mean x to the negative 3rd. So now the idea is we would like for 1 over x to the 3rd to be equal to x to the negative 3rd, because we want this exponent rule to always work. Okay, so the idea is out of this you kind of get this other rule which says that if you have this, an expression that's like 1 over x to a power, that is the same as saying x to the negative n. So 1 over x to the n is the same as x to the negative n. And we're going to have to kind of keep that in mind when we're going down below to be evaluating these two functions for negative exponents. Okay, so now we're going to examine a little closer two examples of exponential functions that are two different forms. So So on the left we have f of n equals 2 to the n. That's the same function we had on the previous page. And we know this is going to be exponential growth here. So I'm just labeling it. And we can kind of remember what we did on the previous page, right? We started with 2 to the 0 being 1, and you can think about your multiplication once again. So you get 1, 2, 4, 8, and then you think about your division going backwards. And you get 1/2 and 1/4. Now I just want to remind you, now you could also think about, instead of the division, you can think about this being 2 to the negative 1 power, which is the same as 1 over 2 to the first power, right? So that's 1/2. And 2 to the negative 2 power is equal to 1 over 2 squared, which is 1/4, right? Okay, so now if we go to plot this on the coordinate plane, just so we get a visual, it's going to be the same as the one on the previous page, but we're going to be comparing it to a different function now. So I have 0, 1, 1, 2, 2, 4, 3, 8, and I'm also estimating the negative 1, 1/2, and negative 2, 1/4, and then I can kind of sketch the curve. Okay, so now let's do the same thing for this new function, which is 5 times 1/2 to the n. Okay, so let's start again with 0 because that's kind of an easy place to start with. So here we do 5. If we do it explicitly, I'm doing 5 times 1/2 to the 0 power. But I know 1/2 to the 0 is just 5. Or sorry, it's just 1. So then this is 1 times 5, and I get 5 here. Now, when I plug in 1, it would be 5 times 1/2 to the first power. So that would be 5 divided by 2, which is 2.5, right? Now I could also start thinking about this recursively by thinking it's going to be repeated multiplication by 1/2. So I could like take 2.5 and multiply it by 1/2 to get my next number. So whichever way you prefer, this is going to end up being 5/4, which is 1.25. And this would be 5/8, which is 0.625. And now if I work my way backwards, instead of, like here I was multiplying by 1/2, right? So then I would need to be going backwards and think dividing by 1/2. But dividing by 1/2 is the same thing as multiplying by 2. So that's actually a little bit easier, is to think I'm going to multiply by 2 to get my previous number. So that would be 5 times 2, which is 10. And then I multiply by 2 here to get the previous number before that, which would be 20. So I could also think about this using negative exponents and think this is 1/2 to the negative 2. Sorry, I'm kind of low on space, so it's like 5 times 1/2 to the negative 2. So that means I would flip the 1/2 and would become a 2 squared, which is 4, so this would be 4 times 5, which is 20. Okay? If you're not understanding that negative exponent stuff, don't worry too much about it. So from here, I'm going to plot my points. So on my y-axis, I actually can't get up to all the way to 20. So I'm going to start with the negative 110, which is right there. Then I have 0, 5. One, 2.5. So there are my points, and now I'm going to sketch my curve. And we can kind of see that now my exponential function is decreasing. So this is called exponential decay. So let's label this above the graph, or sorry, table. Okay, so just a couple of more notes to write at the bottom of this note sheet. we're going to kind of formalize our understanding of an exponential growth versus decay function and what the difference is in terms of the equation. So first of all, we say an exponential function is any function of the form f of x equals a times b to the x. So this is the same kind of form we had on the front page of our notes, or on the first page of our notes. But we're going to be a little more specific about a and b now. So we're going to say where x is a real number and a is not 0. We don't want a to be 0 because if a is 0, then we're multiplying our growth by 0, so we just end up with a constant function of 0. And we also have some restrictions on b. We're going to say b we also don't want to be 0 because if b is 0, we have the same problem. We just have a constant function at 0. But b also can't be 1. And we say that because if b is 1, then we're repeatedly multiplying by 1. Nothing's changing. It's not actually growth, right? Or decay. We just have a constant function once again. And then the last thing we're going to say about b is that we want it to be positive. So I'm going to say b is greater than 0. Basically, I don't want b negative because if b is negative, then what you're repeatedly multiplying by is going to alternate between a positive and a negative number back and forth, depending on if you're doing an odd or an even power. And we don't really want to deal with that. It's not going to actually appear exponential on the graph. So just on the very bottom of your page, we have one more thing to think about, which is that how b affects whether you have exponential growth or decay. So I'm going to kind of graph the values of b on the number line, and then we're going to think about when is growth and when is decay. So remember that b can't be 0, right? So I'm going to plot 0 and plot 1. So we have like an open circle at 0, an open circle at 1. And then b can be between 0 and 1, which is all that stuff, and b can also be greater than 1. That's everything. Oh, actually, I want to do that in a different color. Right, so we kind of get these two areas. And as it turns out, one of them ends up being growth and one is decay. So if b is between 0 and 1, that's going to mean we have exponential decay. And we call that the decay factor. We call b the decay factor. And then some examples would be something like y equals 1/2 to the x, or even, actually I'm going to write it as a decimal because you sometimes see these as decimals. You'll see like 0.5 to the x, or y equals 5 times like 1/3 to the x. So a could be a whole number, but just not b. And then for values greater than 1, we end up with a growth factor. So some quick examples would look like y equals 3 to the x, or y equals 1/2 times 5 to the x. And we'll be practicing with this tomorrow in class.